Hello, ladies and gentlemen, and welcome back. Root Beer here, looking at question number 2 on the 2017 Euclid contest. That's the grade 12 scholarship paper. So let's dive in. Each question worth 10 marks. Hopefully we can get 10 out of 10. We got 3 parts here for question 2. 2 light bulbs and 1 where we need to justify what we're doing to get the answer. So we'll focus on 2a. What are all values of x for which x isn't 0, x isn't 1, and this equation holds true? Okay. So we'll copy that equation down. X minus 1. I think it was 1 over x plus or minus. It was plus. Okay. All right. So what can we do? Well, I don't like fractions. A lot of people don't like fractions. So let's get rid of fractions by multiplying both sides by x times x minus 1. So we'll get 5 here. And we'll get 1 x times x minus 1 over x here. And 1 x times x minus 1 over x minus 1 here. Now this x and this x will cancel out. The x minus 1s will cancel out. So I'll be left with x minus 1 plus x, or 2x minus 1. Well, so if we rearrange, we'll get 6 is equal to 2x, or x is equal to 3. So that's the only time this is going to happen. And if we wanted to, we could double check. 5 over 3 times 2, so 5 over 6 is 1/3 plus 1/2. Yeah, that's true. Okay. So, and we could do that. We could multiply both sides by that because x isn't 0 or 1. So this expression on the bottom here isn't 0. Alright, so B part. In a magic square, the numbers in each row, the numbers in each column, and the numbers on each diagonal have the same sum. In the magic square shown, what are the values of A, B, and C? So we need 3 numbers. I'm betting this is at least worth 3 marks here for our A, B, and C. Well, let's copy it down. We were missing some numbers, although we do have a full column here. So that should be helpful. I think it was 20. It was A. I think C was here. I think B was down here. And I think it was 0, 4, and negative 12. Let's see. 0, 4, and negative 12. Fantastic. All right. So we know it's a magic square, so the sums are the same. So what's the sum here? 20 plus 4, 24 minus 12. It all adds up to 12. So each row, each column, everything's got to add up to 12. All right. Well, I notice I've got a diagonal here. So this produces an equation involving B. 0 plus 4 plus B must be 12. Well, that means B is going to have to be 8. All right. What else can we do? Let's see here. We know B is 8, so now we know blank is, let's call it D, I guess. D minus 12 plus B is 12, but B is 8. So bring the 12 over to the side, bring the B to the other side. D is going to have to be 16. And now I've got 0, C, and D. 0 plus C plus D is 12. But that's 0 plus C plus 16. C plus 16 is 12. C is going to be negative 4. Okay. And, oh, I completely forgot we have this top equation right here. I thought I was going to have to go over and get this one right here, but we don't need that. 0 plus 20 plus A is 12. A is going to be negative 8. And just for completion, we can figure out, well, 8 and the negative 8 will cancel. This guy here has to be 12. Nice. And we could double check A plus 4, so negative 8 plus 4 plus 16. 4 plus 16 is 20, plus negative 8, yeah, that really is 12. So A is negative 8, B is 8, and C is negative 4, and that is our answer to B part. Alright, one more part to go, and we'd actually have to justify for this one. And C part, and it looks like they've snuck in 2 parts here. So this is really an A, B, C, and a D, but that's okay. So C, for what positive integer n is 100 squared minus n squared equal to 9,559? Well, I notice on the one side I've got difference of squares. So we'll start with this equation. 9559. I can factor this side as 100 minus n, 100 plus n. So this is a nice little difference of squares. A nice little factorization that you should know. A squared minus b squared can be written as a plus b times a minus b. This is a very nice little trick, and it comes up a lot on contests. Okay, but n is a positive integer. So 100 minus n and 100 plus n are ints, are integers, and therefore 100 minus n, 100 plus n are factors of 9,559. In particular, 100 plus n is going to be positive because they told us n is positive. So this is positive. Positive divided by a positive, this is also going to be a positive. We can even write that. (9,559) over 100 plus n is also going to be positive. So what does that tell us? N is less than 100. Okay. So this is going to be pretty important. Now, 9,559, I haven't a clue what the factors are there. So let's figure some of them out. It's not going to be divisible by 3 or 5, but maybe divisible by 7? No, not divisible by 7. How about 11? Ah, it is divisible by 11. So it's 11 times 869. And I'm just using my calculator to do that. I'm just trying powers of primes here. Or not powers of primes, just trying different primes. 869, is that also divisible by 11? It is. Fantastic. So we can actually write 11 squared times 79. And 79 is a prime as well. Okay. So 9559 has factors 1, 11, 79, 869. Oh, let's not forget 121. 869 and 9559. Okay. Now, 2 of them need to add up to 100. So 100 minus n plus 100 plus n is equal to 200. So we're looking for 2 factors that add up to 200. So obviously these guys are out, as are these 2. The only factors that allow this is the pair 79, 121. So, flipping the page, so 100 minus n is 79, 100 plus n is 121, and from there we conclude n is 21. If you wanted a more exact way, take this equation and subtract the second equation. You'll get 2n is 42, divide by 2 to get n is 21. But there we go, we have our answer. Alright, so that was C1. Now let's do C2, which really should just be question D. Determine one pair AB of positive integers for which A is greater than 0 or greater than 1 and B is greater than 1, and AB is. That seems kind of silly. I mean, I guess it's question 2, so they still have the kid gloves on, but sure. One pair of positive. This seems kind of silly, but we went through this. AB. Heck, I'll list them all out for you because I just did that a second ago. We could have 11 and 869, We could have 79 and 121, and we can have the reverses of each of these. They're not going to take off marks because they asked for 1 and I gave them all 6 pairs. I mean, they're all there. So, okay, I guess this is justifiably a part 2, although I don't even see why this is even here. I suppose maybe to give you a hint as to what to do with the difference of squares, but I don't know. It just seems like odd test design to me, but let's ignore it and move on to question number 3. So thank you guys for watching. I'll see you next time.